Hi, hello students. Today we'll discuss about the topic RF amplifiers and matching networks. So in this topic we are going to discuss about how the microwave amplifiers will work and what is the construction and what are the characteristics and what are the parameters which affect the amplifier. All those things we'll discuss now. So see here, this is the complete amplifier block, and here we have this amplifier system. It is represented by the S matrix, and here we have RF source, and this is the load is connected. Between RF source to amplifier we have input matching network. It is going to match the impedance between RF source to amplifier, and there is another matching network is connected between amplifier to load. So this is going to match the impedance between load to the amplifier. And for this amplifier the DC bias is required, which is provided over here, and these are the corresponding reflection coefficients. The gamma S is for source, gamma N is input reflection coefficient of amplifier, gamma L is load reflection coefficient, gamma out is output reflection coefficient of the amplifier. So now we will discuss about what are the characteristics of amplifier. Before that, what are the key parameters available, right? Gain and gain flatness, that is indicated represented in dB, operating frequency and bandwidth in hertz, output power in dBm, power supply requirement in volt as well as ampere, input and output reflection coefficients in terms of VSWR, noise figure in terms of dB. So these are the key parameters. And what are the parameters which affect amplifier performance? So these are the four major parameters which affect the amplifier performance, that is, which affects the above terms, that is intermodular distortions, harmonics, feedback and heating effect. So we are going to use this amplifier in high frequencies, and these are the parameters which affect easily the amplifier performance in microwave frequency range. And the above amplifier has been, the block diagram of the amplifier has been reduced into these following relations, that is with the help of power relations. So this is a simplified schematic of a single stage amplifier, and which has two ports, port number 1 and port number 2, and port number 1 is for input, port number 2 for output, and this has been reduced into this stage that we are going to represent by taking the input side, and we are going to take only the nodal analysis. With the help of nodal analysis, here the term A represents incident wave, B represents reflected wave. The 1 represents port 1, the 2 represents port number 2. So with the help of this nodal analysis, we are going to simplify, with the help of signal flow graph, we are going to simplify the entire structure like this, and from here we are going to take the input path. It has been reduced into these structures. Okay, this is a source and load connected to a single stage amplifier network. Like see here, the source signal can be represented by taking this voltage divider rule, that is root of Z0 by Zs plus Z0 into source voltage, that is equal to B1 dash minus A1 dash gamma S, that is equal to B1 dash, if we take it as common, then B1 dash of 1 minus gamma in gamma S. It has been taken from this signal flow graph. So BS equation we have taken over here. Then this is the incident power, that is equal to B1 dash whole squared by 2. So B1 dash we are going to calculate from here and substitute this, we will get equation number 9.2. Then the relation for input power is equal to, this is incident power, this is input power to the amplifier, that is equal to incident power of 1 minus gamma in whole squared. So we are going to substitute this P incident value of 9.2 here, then we will get 9.3 equations. Then PA is the available power in the amplifier. The formula is equal to input power, then replacing gamma N is equal to gamma S star. So you have to substitute the input power relations, that 9.3 over here, then we will get what is the available power in the amplifier, that is equal to 1 by 2 times BS squared by 1 minus gamma S whole squared. So 9.4 is the available power of the amplifier. From this we are going to calculate what are the gain relations available. So transducer power gain is equal to power delivered to the load by power available from the source. So PL by PA, where PL equation is equal to 1 by 2 times B2 squared. So B2 is nothing but that is reflected power in port 2, that is multiplied with 1 minus gamma L whole square. So we substitute PL over here. PA already we have derived, that is equation number 9.4 is PA equation, that is available power. PL is here, so we have to substitute both the cases over here, then we can get transducer power gain. So transducer is equal to PL by PA, that is equal to B2 squared by BS squared of 1 minus gamma L squared into 1 minus gamma L squared. It is equation number 9.5. It is the transducer power gain. So here we are going to calculate what is B2 by BS ratio. So by taking S parameter derivations, we have to calculate B2 is equal to S21 A1 by 1 minus S22 gamma L. Similarly, this is BS equation. By taking the ratio B2 by BS, we will get equation number 9.7. And then equation 9.7 can be substituted over here. Then we will get the final stage of transducer power gain. So here we are going to replace these B terms in terms of reflection coefficient as well as S parameter. For that we are going for this. So take a ratio of 9.6A to 9.6B and you will get the equation number 9.7. So 9.7 can be substituted in 9.5 instead of this B2 by BS. So after substituting we will get this is the transducer power gain relations where gamma N is equal to S11 plus S21 S12 gamma L by 1 minus S22 gamma L, whereas output reflection coefficient is equal to S22 plus S12 S21 gamma S by 1 minus S11 gamma S. So these two cases we are getting from this amplifier relations. Then after substituting we will get the overall transducer power gains by equation number 9, 10 as well as equation number 11. Then the unilateral power gain is nothing but we are going to consider the power travelling from 1 to 2, not in the reverse. So if we take power travelling from port 1 to port 2, then it becomes unilateral power gain. Then the available power gain is nothing but GS equal to, in the transducer power gain, we are going to replace gamma L is equal to gamma out star. So if we replace this, we will get equation number 9.13. This is called as available power gain. So the overall operating power gain is equal to power delivered to the load by power supplied to the amplifier, that is PL by PN. So PL by PN we are going to multiply PA in both numerator as well as denominator. Then we can separate PL by PA can be GT. Then we have PA by PN. So GT already we derived, PA already we derived, PN already we derived, that is equation number 9.3, 9.4, 9.10. So we substitute all these things, we will get the overall operating power gain G is equal to 1 minus gamma L squared into S21 squared by 1 minus gamma N squared into modulus of 1 minus S22 gamma L whole squared. So this is the overall operating power gain. Thank you.